You know that feeling when you're working with an LLM? Maybe you're pasting in a massive code base, or a 50-page legal contract, or a whole novel. And you hit enter, and it processes a million tokens of context. But then, it drifts. It forgets the instruction you gave it 3 paragraphs ago. Or worse, it starts hallucinating details from the middle of the text that aren't actually there. We tend to think of this as a bug, or just a limitation of the current model version. We tell ourselves, oh, GPT-6 will fix this. But it's not a bug. It's actually a fundamental law of the architecture we're using. The transformer, the engine behind GPT, Claude, Gemini, has a dirty secret. It doesn't actually remember anything. It fakes memory. Every single time it generates a new word, it has to reread the entire conversation history from scratch. It's like a pianist who can only play the next note of a song if they replay the entire song from the beginning every single time. It works. Obviously, it changed the world, but it's incredibly inefficient. It's like driving a car by rebuilding the engine every time you press the gas pedal. And right now, that inefficiency is the single biggest wall standing between us and the next leap in AI. So, let's talk about what comes next. I want to show you the 3 architectures that are trying to tear that wall down: the snake, the hybrid, and the liquid. Before we look at the solutions, you have to understand exactly why the transformer is hitting a ceiling. It comes down to one specific piece of math that we call the attention mechanism. Now, standard tutorials will show you a matrix multiplication and call it a day. But that doesn't explain the pain. Here's the tricky part. And honestly, the way I like to visualize this is to think of a crowded networking event. In a transformer, every single word, or token, is a person at this party. To understand the context, every person has to shake hands with every other person in the room. If you have 5 people, that's manageable. 25 handshakes. But if you have 1,000 people, that's 1,000,000 handshakes. If you have 100,000 people, this is the quadratic bottleneck. But there's a second bill in here that nobody talks about, the KB cache, the key value cache. Because we don't want to recalculate those handshakes every millisecond, we store the results in GPU memory. That storage is the KB cache. As your conversation gets longer, that cache gets massive. It eats up your VRAM. Eventually, you run out of physical space on the chip. That is why your infinite context model actually has a limit. It's not a creative choice, it's a physics problem. We need a way to stop shaking hands with everyone. We need a way to walk through the party, remember the vibe, and move on. This brings us to contender number 1, Mamba. Mamba is built on something called a state space model, or SSM. Now, historically, SSMs were great at simple signals, like tracking the temperature of a sensor over time. But they were terrible at language, they couldn't focus. Mamba changed that. Here's the mental model I use for Mamba versus a transformer. Think of the transformer as a librarian. When you ask a question, the librarian runs down the aisle, pulls every single book you've ever mentioned, lays them all out on the table, and reads them simultaneously. It's accurate. But it's slow and messy. Mamba is not a librarian. Mamba is a scanner. It reads the text once from left to right. As it reads, it updates a tiny compressed summary in its pocket. This summary is called the hidden state. Once it reads a word, it throws the word away. It only keeps the summary. But wait, how does it know what to keep? That's the magic. That's the Mamba part. It's called selectivity. Standard state space models treated every word equally. The was just as important as nuclear. Mamba adds a gate. I like to think of this gate like a bouncer at a club. A word walks up to the door. The bouncer looks at it. If the word is or like, the bouncer says, not tonight. It deflects it. The memory state doesn't change. But if the word is recipe or password, the bouncer says, you're in. It opens the door, and that information gets written into the permanent state. Because of this bouncer, Mamba effectively has infinite memory. It doesn't need to look back at the past because the important parts of the past are already compressed in its pocket. It's O of n linear. You can feed it 1,000,000 tokens, and it processes them as fast as 10. Next up is RWKV. If Mamba is a scientific breakthrough, RWKV is a brilliant engineering hack. In the deep learning world, we've always had this painful trade-off, almost like a pick-2 triangle. You can have an RNN, a recurrent neural network. These are super fast to run because they just loop over themselves, but they're a nightmare to train. You can't parallelize them. You have to wait for step 1 to finish before you can train step 2. Or you can have a transformer. Amazing to train because you can feed the whole internet into it at once. That's parallelism. But heavy and slow to run. RWKV asks, why is this a choice? The way I wrap my head around RWKV is by thinking of it as a transformer in disguise. During training, it unrolls itself. It looks like a transformer to your GPU. It uses the same parallel math, so you can train it on massive clusters of H100s efficiently. but the math is constrained. They tweak the attention formula just enough so that it relies only on the previous step. So when you're done training and you want to run it on your laptop, snap. It rolls up into a tiny RNN. This means you get GPT-level smarts, but you can run it on a consumer CPU without needing 100 gigabytes of RAM for that KB cache we talked about earlier. It's the ultimate have your cake and eat it too architecture. Finally, let's talk about the wild card, liquid neural networks. The first two, Mamba and RWKV, are trying to optimize the math we already have. Liquid networks are trying to rewrite the rules entirely. They're inspired not by statistics, but by biology. Specifically, the brain of a tiny worm called C. elegans. Here's the fundamental difference. Most neural networks are frozen. You train them, you save the weights, you deploy them. Whether it's raining, snowing, or the camera is broken, the network uses the exact same static weights to make a decision. Liquid networks are, well, liquid. They're time continuous. This part is tricky, so let's use a driving analogy. Imagine a standard neural network driving a car. It takes a snapshot of the road every 1 second. Snapshot, steer, snapshot, steer. If the car suddenly speeds up to 200 miles per hour, the network might crash because the world changed too much between snapshots. A liquid network doesn't take snapshots. It solves a differential equation. It describes the motion of the car continuously over time. If the car speeds up, the network adapts its internal time constant. It effectively thinks faster. If the car slows down, the network relaxes. This makes them incredibly robust. MIT researchers showed that a liquid network could pilot a drone in heavy rain and wind, even though it was only trained in clear weather. Why? Because it understood the causal physics of flight, not just the statistical pattern of pixels. So, where does that leave us? Are transformers dead? No, not yet. The transformer has something these models still struggle with: recall precision. When you absolutely, positively need to remember the 57th word on page 302, the transformer's brute force approach is still king. But the monopoly is cracking. I think the future isn't going to be one single architecture that rules them all. It's going to be a hybrid system. We're already seeing this with models like Mamba from AI21 Labs. It uses Mamba layers to handle the massive context, reading entire books cheaply. And then it sprinkles in a few transformer layers to do the heavy reasoning where it counts. We're moving from the era of bigger is better to the era of smarter is better. We're breaking the quadratic bottleneck. And once that wall is down, the definition of what AI can remember changes forever. Thanks for watching. Catch you in the next one.